Hello dear friends, myself DipaliWarade from Professor Ramakrishna More Arts, Commerce and Science College. Today I am going to discuss one of the important topics from theory of computer science, that is a context-free grammar. In context-free grammar, after watching this session, what a student will get. So first you will get a grammar's definition and examples of grammar in theoretical computer science, what is grammar called as. Secondly, Chomsky hierarchy, which is specified by Noam Chomsky and contains types of grammar in theoretical computer science. Fourthly, a context-free grammar, and lastly, ambiguity in a grammar. So first we will see the definition of grammar. So what is grammar? A grammar G can be formally written as a four-tuple B, T, S and T, where B is a set of variables or non-terminal symbols. So all the non-terminal symbols in a grammar are specified by a capital alphabets. So every symbol in a set V is a capital letter. Secondly, a T or summation is a set of terminal symbols. All the terminal symbols are specified by small letters in a given grammar. So every symbol in the set T is a small alphabet. Third is a S. S is a special variable called a starting symbol, and S belongs to V. So S must be in from the set V, that is a capital letter. Last and important, P is a production rule for terminals and non-terminals. So P is made up of combination of terminals and non-terminals and has the form alpha gives beta. So alpha can be combination of terminals and non-terminals. Also beta can be a combination of terminals and non-terminals. It is specified by V union summation, that is a combination of non-terminals and terminal symbols. And one more important thing is at least one symbol of alpha belongs to V. Means on the LHS of the production rule, a one non-terminal symbol must be present. Then only it is called as a grammar. We will see example of a grammar. Then we will understand more about it. So first example we will see. It is written in a round brackets. Round brackets, there are four tuples you can see. First is a curly bracket S comma A comma B. So S comma A comma B is a set V, and as we know from a definition, S, A and B are non-terminal symbols. Second set is A comma B. From definition we know that all the small letters belongs to terminal symbol, so that A and B is a set of terminal symbols. S is a starting symbol. S is a capital letter. It belongs to set V. So it is also following our definition. And last curly bracket contains three production rules of the form alpha gives beta. S gives AB, A gives A, and B gives B. Uh, Note that LHS of every production rule is having a capital letter in it according to our definition. That is, a non-terminal must be there on the left hand side of the grammar, and right hand side you can do any combinations of small letters and capital letters, that is terminals and non-terminals. So these are the productions. We will see one more example of the same type, grammar G2 we can call it as. It is again having four tuples. First tuple is SA, that is a set of non-terminal symbols. Second tuple is again A comma B. A and B are terminal symbols. Third is S, that is a starting symbol. And the last set is of production rules, that is S gives AAB, AA gives AAAB, A gives epsilon. Uh, these are the production rules. So next we will see a Chomsky hierarchy. So according to Noam Chomsky, there are four types of grammars: type 0, type 1, type 2 and type 3. So we will see one by one. First is a type 0 grammar, that is recursively enumerable language. So the recursively enumerable language generated by a type 0 grammar. So the type 0 grammar is also known as unrestricted grammar. It is called as unrestricted grammar because there are no restrictions on the grammar rules of this type of languages. Means LHS and RHS can be made by any combination of terminals and non-terminals. There is no restriction on how the LHS is written or how the RHS is written. The only compulsory rule is that on LHS, one symbol from non-terminal set should be there. These types of grammar are accepted by Turing machines. Next, we will see the second type of grammar, which generates context-sensitive language. So it is also called as a type 1 grammar. So type 1 grammar is known as context-sensitive grammar, as it generates context-sensitive language. The context-sensitive grammar is used to represent context-sensitive language. So there are four rules for type 1 grammar. We have seen type 0 have no restriction, but type 1 grammar have four restrictions. The first is that the context sensitive grammar may have more than one symbol on left hand side of the production rules. So on the LHS, more number of symbols can be there. Second rule is that the number of symbols on the left hand side must not exceed the number of symbols on the right hand side. Now you can see in the example, first production I have written S gives 80. Second production is 80 gives XY. This is a valid production rule as uh, there are two symbols on the left hand side and two symbols on the right hand side. It is not exceeding, LHS is not exceeding the RHS symbols. But you can see the last production, that is 80 gives X. So 80 gives X. In LHS there are two symbols, but in RHS there is only one symbol. So this is not allowed according to the rules. So this second rule is specifying that on the LHS more number of symbols can be there, but condition is that on the RHS the symbols must be greater than the LHS. The third rule is the rule of the form A gives epsilon is not allowed unless A is a starting symbol. Means A gives epsilon is allowed only when A is a starting symbol. So in the given grammar of example, S is a starting symbol as you can see. So A gives epsilon is not allowed. As A is not a static symbol in this given grammar, S is a static symbol is in this grammar. So gives epsilon is not allowed as it is not a static symbol. Last, the type 1 grammar should be of type 0. In the type 1, production is in the form V gives T, where the count of symbol in V is less than or equal to T. This is a type 1 grammar. Now we will see the next type, that is a context free, or we can call it as a type 2 grammar, that we are going to discuss more in this chapter 4. So type 2 grammar is known as context free grammar. It generates context free language. Type 2 grammar should be of type 1. The production rule is of the form A gives alpha, where A is a single non-terminal and is any combination of terminals and non-terminals. So A gives A, B, B. A gives B, B gives A. So you can see on the left hand side there is a single non-terminal, and on the right hand side it is alpha, and alpha can be a combination of any terminals and non-terminals. There is no rule. But on the LHS there should be a single non-terminal. Then third type is a regular grammar. It is also called as a type 3 grammar. It generates language called as a regular language. The regular languages are those languages which can be described using regular expressions. And these languages can be modeled by finite automatons. So type 3 is the most restricted form of grammar. Type 3 grammar should be of type 2 and type 1, and type 3 should be of the form V gives T into V or T star, means a combination of T and V or T star. A simple example is A gives XY. As it is the type 3 grammar should be of type 2 and type 1, all the rules of type 1 and type 2 must be followed by type 3 grammar. So this is a Chomsky, Ratche and all the 4 types of grammar from which we are going to see context. So we will see the definition of context-free grammar. So what is context-free grammar? It is again a quadruple VTPS. So what is V? It is a set of non-terminal symbols as we have seen in a definition of grammar. T is again a set of terminals. V intersection T equals to null. Means V and T must not have a common symbols in between them. T is a set of rules. T should be of the form N gives V union T closure. So what is its meaning? N is a single non-terminal gives V union T closure, means 0 or more symbols from a set V union T. 0 means N gives epsilon. So if it is N gives epsilon, means it does not have gives, means N does not gives any symbols from V and T. And lastly, S is a starting symbol of the given grammar. First example, first is A, so it should be a set of non-terminal, that is a V set. It is having only one symbol, that is A. Second set is of terminal symbols, that is a set T. It is having three symbols A, comma B, comma C. Third is a starting symbol, that is A. As we know that starting symbol should be from set B and it is only one symbol in set B. So the starting symbol is A. And last set is of the productions, which of the form N gives V union T. We can see it is a combination of V and T, that is a capital A from set V and small a from set T. Second is A gives ABC. It is left hand side is N, that is a non-terminal symbol, and right hand side it is a terminal symbols. So this is example 1. Second example, first set, that is a set of non-terminals, it is having SAB. Second set, which is of the terminal symbols, is A comma B. Third tuple is a starting symbol, that is S. And last is a set of productions. S gives ASA, S gives BSB, S gives epsilon. See here, S gives epsilon means uh, S left hand side single non-terminal, and right hand side no symbol from set V or no symbol from set T. So it is indicated by a null production, that is the epsilon production. So next we will discuss what is ambiguous grammar here, its definition and examples. So what is ambiguous grammar? See, in a context-free grammar, which is indicated by G, if more than one derivation of some string is there, it is called as an ambiguous grammar. Means the same string, it is deriving in a two methods, or it is having a two derivations, then it is called as an ambiguous grammar. Uh, from definition, we can see that there exist multiple rightmost or leftmost derivations for some strings generated from that grammar. Means for a single string, if there are two parse trees, then it is called as an ambiguous grammar. With example, you will be more understood this concept. So example we will see. Example 1. Check whether the grammar G with production rules x gives x plus x into x or a is ambiguous or not. So we have to check whether the given grammar is ambiguous or not. So what is the solution for this? Let's find out the derivation tree for a string a plus a into a. It has two leftmost derivations. We will see one by one. So derivation 1, we have written given production first. X gives x plus x. We have given with the string a plus a into a. So a plus a is indicated by x plus x. So x is changed by a, or we can say derived by a. So next step is a plus x into x. For x we can write x into x from the given production rules. For x we can write x into x. We are doing this from this given string. We have to derive a plus a into a. So we have written x into x for this x. Now we will change, or we will derive a for this x, and next step we will write a for this remaining x. So this is a derivation, and we can draw a derivation tree from this derivation. So first what will be in a derivation tree, the left hand side, that is x, then right hand side x plus x. So what the first symbol from will be x, then plus, this x is derived by a as per the derivation, then plus and x. So now this x will be written as x into x. So in a derivation tree, likewise x into x. Now the left hand side x, that is this x, will be derived as a, and then right hand side x is derived as a e. So this is the derivation tree for the derivation 1, and now we will see the derivation 2 for the same string. Derivation 2, so x gives x into x. Now see, for in the first derivation we have taken x plus x, and in the second derivation we have taken x into x, and we are going to derive the same string again. So x into x, so we have written for the first x, x plus x, then x for x, we have written a, or we have derived a plus x into x, then a plus a into x, a plus a into a. So we have derived the string from the given expression in the second format, that is we have taken x into x first, and then same string is derived. For this, derivation tree will be x into x, so it is proved that for the given string, the grammar is having a two derivation trees. So this grammar is an ambiguous grammar. So friends, thanks for watching. This is just an introductory part of chapter 4, that is context-free grammar. In next session, we will see how strings are derived, or how past trees are drawn from a given string and from a given context-free grammar. Thank you.